Let's wait for 2 3 minutes and then I will start. Okay. Switch off the video. Right. So today this is uh, week 11 problem solving session. So what we will do today is that we will start with the assignment questions. So there are this time some 10 assignment questions are there. This is related to week 10. That is the based on the concept of dummy variables. And once this is finished, we'll solve all these questions in details. And then what we will do is that we will come to the week 11 concepts which are there. Some important concepts I have chosen, which is important for solving uh, the assignments of the week 11. So those things we will see, those concepts we will see, and based on those concepts, we will try to solve few problems. So that will give an idea that how to solve those problems. And of course, in the next week, I will solve those week 11 assignment questions. Right, so this is the plan today. Okay. So the first is that we will do the assignment questions of week 10. Number two is the week 11 concept, which is based on the polynomial regression. We will see some important concepts. Not everything we will discuss because several things are being solved in the video lectures. So you can always follow them. That is very nice. And after this week 11 concept, we will practice some questions. Okay, so this is the in total plan. So without any delay, let us start the assignment problems. Change the color. Let's look at the assignment question for week 10. Okay, so the first question of the assignment, let me open it. Yes, a dummy variable is used as an independent variable in a regression model when. So there are so many things are there. So when does this dummy variable is used? Is because when you see that the variable or the data set is some kind of a categorical, means a qualitative kind of a thing, then only we will use. So the variable involved is categorical. So it is, remember, what do you mean by categorical is that, so categorical means that yes or no kind of a thing. Okay? So just remember that whenever we have used a two dummy variable concept, so whenever we have used a two dummy variable concept, just remember the last lecture. So we have used a variable, dummy variable z. Of course, there is another variable x naught, where the values of x naught were always 1. Whereas z, that is this dummy variable, it always takes either 0 or 1. That is either no or yes. This kind of a thing, a binary kind of a thing, either 0 or 1. So this is actually called the categorical kind of a variable. Okay. So that's why these dummy variables, which is asked in the question, you can see that a dummy variable is used as an independent variable in a regression model, which we have used so far. That is when the variable is involved is categorical. So that is what the first question is. If a categorical independent variable contains three categories, these three categories are what we have seen the sets A, set B, set C in case of three dummy variables case. Then the number of dummy variables excluding x naught will be needed to uniquely represent these categories are is. So how many dummy variables are required is the question, right? Just a minute. So how many dummy variables are required? So that is what is asked. And it has been already given in the question that there are three categories. Okay, so let's come to the solution. So you have three qualitative data or three categories or sets, whatever you wanted to say, three categories or sets of data. So you know that the number of sets of data, generally we use that number of dummy variables. So the number of dummy variables in this case should be equal to 3. But this number of dummy variables, total number of dummy variables includes x naught and two actual dummy variables, right? This is also dummy. But this is this kind of a dummy variable we always use. We don't show, but we always use, right? Because its value is always 1. So excluding x naught which is one of the dummy variables, no doubt. So excluding x naught, there will be then how many? Two dummy variables are involved in three categories of data. So two dummy variables. Right. So this is two is the correct answer for this particular question. Right? Answer is two. Okay. Let's go ahead. Third question shows that you have two sets of data involving x and y, but you are unsure whether to fit the data separately or together. You consider and fit 8 parameter model. All parameters you have taken. That is what we generally take for the dummy variable case. Yeah, so z is the dummy variable whose value is 0 for set A and 1 for set B. We have seen these things. Now, question is that what hypothesis would you test to answer the question that will a single quadratic model fit all the data? Single quadratic model, which we will see today actually, quadratic model. We have seen also just a glimpse is being given in the week 10. Quadratic model means this up to this alpha naught plus alpha 1x plus alpha 2x square. That's all. That is the quadratic model. Now, if you have the total data, say if you have 8 parameter model like this, alpha naught plus alpha 1x plus alpha 2 x square plus alpha 3 x cube, which is given in the question, and z, the dummy variable, into beta naught plus beta 1 x plus beta 2 x square plus beta 3 x cube and plus etc. So this is the generalized model. Means it can be possible that if you have different qualitative data like a set A and set B mentioned in the data set, you can write it as a generalized expression. Now it has been asked that single quadratic fit. You have to test for single quadratic fit. So if you have single quadratic fit, that means that only this part has to be there. So single quadratic fit means y is equal to alpha naught plus alpha 1x plus alpha 2 x square plus epsilon. This is the quadratic fit model in general, quadratic fit model. But if you require a single quadratic fit model, then all other coefficients must be zero. Then only we will have this kind of a single quadratic fit. We don't want beta naught plus beta 1x plus beta 2x square, right? Then because if we keep these beta naught, beta 1 and beta 2, then what will happen? There will be two quadratic fits for different data sets. So for single quadratic fit, the model should be like this. Now you have to test for this. So what will be your null hypothesis? Your null hypothesis will be you keep alpha naught, alpha 1 and alpha 2 and all other parameters to be 0. So alpha 3 is equal to beta naught is equal to beta 1 is equal to beta 2 is equal to beta 3. All this equal to 0. This should be your null hypothesis. Okay, the idea is clear. Now, what about H1? H1 is that this H0 is not. Okay, so this is how the test has to be designed based on whatever is asked. Okay, so this idea is clear now. Fine. Now, how to test it? To test it, you will use the extra sum of square technique we have seen in the last class. How to do it? Extra sum of square we have seen earlier also for the full model minus SS regression for the restricted model divided by the degrees of freedom of the numerator divided by the MS residual. Okay, so MS residual for definitely for the full model. So let us talk about the degrees of freedom slightly. Just look at SS total. How many degrees of freedom we have seen that there is only one constant because it depends on only y, right? Y data set. So SSP has only one constant, so it will have n minus 1 degrees of freedom. Correct? We know that. Fine, because this never changes. Okay. What about SS residual? In case of SS residual, we know that number of constraints depends on the number of parameters in the model. Now, see, this is MS residual for the full. So, SS residual for the full model, which consists of how many parameters? 1, 2, 3, 4, 5, 6, 7, 8. 8 parameters. Okay. So it will be n minus 8. This many degrees of freedom will be there. All right. Next, what about the SS regression for the full model? How many degrees of freedom? Simple. It will be degrees of freedom of SSP minus degrees of freedom of SS residual of the full model. Okay. All are degrees of freedom. Remember, this is not actual. Okay. So it will be n minus 1 because degrees of freedom, linear kind of thing, you can add or subtract. Plus, also plus minus n minus n. So it will be n minus 1 minus n plus 8. How many? 8 minus 1, which is 7. So degrees of freedom for SS regression full model is 7. All right. So this is done. This is done. Now SS regression for the restricted model. Fine. For the restricted one, what is the model? It is alpha naught plus alpha 1x plus alpha 2 x square. Single quadratic model. This. How many parameters? 3. Fine. So SS residual. Let us find SS residual first. How many degrees of freedom? N minus number of parameters. 1, 2, 3. This many degrees of freedom for SS residual of the, not the full, but the restricted model. All right. Then what is SS regression? The degrees of freedom of SS regression for the restricted part? It will be SS total n minus 1 degree of freedom minus the SS residual of the restricted part. So this gives you 3 minus 1, which is 2. So 2 degrees of freedom for the SS regression restricted model. Fine. Now the degrees of freedom is calculated. You can just put it like this. So F will be SS regression of full model minus SS regression of restricted model. Now, how many degrees of freedom in the numerator? Full model 7 minus restricted model 2. So 7 minus 2 is 5 divided by MS residual of the full model, which is SS residual of the full model divided by residual degrees of freedom for the full model. How many residual degrees of freedom? It is n minus 8. So this is the extra sum of square statistic, the F statistic. Now this therefore should be equivalent to the F of 5 numerator, comma degrees of freedom in the denominator, which is n minus 8, comma the significance level, either 0.01 or 0.05, whatever you want. So final thing is this. The extra sum of square, the F statistic, should be equal to F, means it should be greater than, F should be greater than F5 comma n minus 8 with whatever significance level you want. Okay. So if this is valid, then H naught can be accepted. That is, what do you mean by H naught accepted? H naught accepted means that single quadratic field. Because in H naught, we have quadratic field. Because in H naught, we have actually put the conditions for the single quadratic model. Correct? So you need the A statistics to be greater than this. So let's come to the question again. Let's see. Okay. So yeah, for the first test, with a single quadratic model, how to test? So you can see that beta naught plus is equal to beta 1 is equal to beta 2 is equal to beta 3 is equal to alpha 3 is equal to 0. This is the null hypothesis. Perfect. And the distribution, fourth question, I have combined both, third and fourth. The distribution of the test statistics to test this hypothesis in problem 3 is F5 in minus 8. Okay, so we have seen how to calculate the degrees of freedom of the numerator to that of the denominator. Simple, with the simple concept we can calculate it. That I have shown. So third and fourth question is done. Okay, so now the fifth question is consider problem 3. What hypothesis would you test to answer the question, will a single straight line model fit all the data? Okay. Now the single straight line, remember, earlier case, single quadratic, but this time, single straight line. Okay. So up to this is third, this is fourth. Let's come to the fifth. Fifth is what? To test for single straight line model. So how much I should take from the original problem 3, this model? Straight line, single straight line. That means this part. Only this part I will take. Alpha naught plus alpha 1x plus epsilon, of course, which is the straight line model. All other terms has to be 0, no doubt. Okay. So let us write, therefore, for the single straight line model, the model will be y is equal to alpha naught plus alpha 1x plus epsilon. This is the single straight line model. You don't need any other variable. Then what will be the null hypothesis? It is all other variables alpha 2 is equal to alpha 3 is equal to beta naught is equal to beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. So all the dummy variable part beta naught, beta 1, beta 2, beta 3 should be 0, and to have a straight line the quadratic term is 0 and the cubic term is also 0. The coefficient of that should be 0, right? And the alternative hypothesis will be H naught is not. Okay. Just the thing is that this should be less than it, right? Then only H naught can be accepted. F should be less than it. Fine. So this is the hypothesis. So fifth question, if you go here, fifth question, yes. So single straight line, beta naught, beta 1, beta 2, beta 3, all the dummy variable part is 0 and alpha 2 and alpha 3 are 0. This is the null hypothesis. And the test statistic to test the hypothesis. So here it is said that only find out the test statistic. You don't need to show the greater or the less sign. All right. Let's look at the test statistic. Simple. We'll go in the same way. If SS regression of the full model minus SS regression of the restricted model. Why am I doing like this? Because to understand what will be the degree of freedom of the numerator divided by SS residual of full model divided by residual degrees of freedom. All right. So for the full model, we have seen that degrees of freedom for SS residual full model, which is having 8 parameters, we have already seen this is n minus 8 because 8 parameters is there. Great. So this is done. Next is SS regression of the full model. This is also we have seen. How many degrees of freedom of the? It is, I think 7, right? Let me check. Yes, it is 7 degrees of freedom. All right, this is done. Next is we need to understand what is the degrees of freedom. Okay, this is also degrees of freedom of SS residual for restricted model. Now the restricted model is different. How much? This. So 1, 2 parameters. So how many degrees of freedom? N minus 2 constants. This is the residual degree of freedom. Remember, for the restricted model. So from here, we can calculate the SS regression degrees of freedom for the restricted model, which is nothing but SS total degrees of freedom, which is n minus 1, always remain the same, minus n minus 2. So how many it will be? 1. Correct? 2 minus 1 is 1. So therefore, in the numerator, the degrees of freedom will be what therefore? So it will be SS regression for the full model minus SS regression for the restricted model divided by. So for the full model degrees of freedom is 7. For the restricted model is 1. So it will be 7 minus 1 divided by SS residual for the full model and divided by the residual degrees of freedom in minus 8 for the full model. Therefore, the f stat this f will be therefore compared to 7 minus 1, 6 in the numerator and the denominator is minus 2 with some significance there. So this should be the correct answer. All right, let's come to the solution. Yeah, 6 comma n minus 8. So this is the right answer. Next is consider problem 3. What hypothesis would you test to verify the models have same slope? Okay, same slope. Okay, let's now come to this. This is, I think, 7, right? So this was 6, yes, 7. Model having same slope, have same slope. You have to test for it. Okay. Now, just I write the entire model again. Alpha 1x plus alpha 2 x square plus alpha 3 x cube plus z into beta naught plus beta 1x plus beta 2 x square and plus beta 3 x cube plus x. Right. So this is the actual model, generalized model. Now, model have same slope. So just consider the slope only. How to put a single slope model? Only by keeping alpha 1 into x, by removing this part, beta 1 into x. So it's a same slope model. Okay, it's the same slope model. It has never said that it's a straight line model or a cubic fit model. So you cannot take so many parameters. It's a single slope model. So therefore, from the dummy part, that is z times whatever in the bracket it is there, from the dummy part, you just remove the another slope which is introduced here. That is the beta 1x. Actual slope is alpha 1x. But so single slope, same slope means single slope. So one of the dummy part, we generally remove it. Therefore, if you remove the dummy part, you have to keep beta 1 equal to 0. All other terms will remain as it is because it's a same slope model. They never told that it's a single straight line model or a single quadratic fit model or a single cubic fit model. Remember? So this has to be taken care. So y is equal to, sorry. So the null hypothesis will be beta 1 is equal to 0. So for the same slope, we keep only alpha 1 and remove beta 1. Then only you have same slope. Just remove the beta 1. Whatever the model you have, will have same slope. Okay. And we generally remove the so the dummy part. Just remember. So H1 will be for beta 1 not equal to 0. Same thing you can do. You can use that extra sum of square technique. It's absolutely fine. So again, if we just write, this will be SS regression of the full minus SS regression of the restricted model divided by the numerator degrees of freedom, that is from the difference whatever degrees of freedom will come, and at the denominator it will be the residual degrees of freedom. All right. So this is degree of freedom residual. All right. So we know that denominator, the SS residual is the full. SS residual full will have degrees of freedom n minus 8. This will not change. Similarly, SS regression full will have degrees of freedom 7. This will also not change. Change will happen in the SS regression restricted. So to calculate that, you can have SS regression. Let us write it directly. Okay. So restricted model, because so this will be degrees of freedom of SS total, which is n minus 1, which will never change, minus SS residual for the restricted model. So in the restricted model, if you remove beta 1, how many parameters will be there? 1, 2, 3, 4, 5. This is not there. 6, 7. So it will be n minus 7. So how many? The 7 minus 1 is 6. So 6 restricted degrees of freedom of the residual regression. Therefore, the F will be SS regression of the full minus SS regression of the restricted divided by the degrees of freedom of this divided by SS residual of the full, and its degrees of freedom is confirmed to be n minus. Okay, so how much is this? This is for the full it is 7, for the restricted it is 6. So this will be equal to f of 7 minus 6 is 1 comma n minus whatever significance that will be 1. All right. So this should be the. I think this is up to this. It is 7. Here it is 8. Just let us see. Yeah. So it will be beta 1 has to be 0 for this, and the distribution test statistic is f1 comma n minus 8. Okay. The next question is, if a data point in a set A and a data point in set B had same x value, would these 2 points be the repeat point in the fit of the model? See, no, never. See, if you repeat the values, the regression model will change. Okay, because as you can see, the mean will change. If you repeat a variable twice in the entire data set, of course the mean will change, and hence all the slope, intercept, whatever the things are there, all these things will change. So you cannot repeat. It has to be used once in any, okay, any set of the data. So its answer should be no. Okay, so I'm not writing. Just let's come to the 10th question. Data on a response y and k predictor variables this arise from two factors. It is desirable to fit a model of the form this which is given here. Just don't worry about this q and all. So where q is equal to a or b, that means that beta naught beta 1 they are of different sets. Means q can be 0, q can be 1 also. Okay. So as you can see here, so 0 0 and 1 0, something like that it will come. Something related to the dummy variable. Here's the factory in which the prediction will be made. In other words, the effects of x2 to xk are same in both factories. So this will not change. So x2 to xk will remain same. But the intercept and the slope with respect to x1 are different for each factory. This problem can be handled by using one dummy variable because there are two sets A or B. So one Z variable is required, okay, which takes the value either 1 for A and 0 for B. Then fit the model. So it is simple actually. So let us write it, whatever the answer or the question is given, and then just easily we'll find out. Okay, let's come to, so the ninth is no, you cannot use it. So 10th is that, so z is equal to 0 for set A and z is equal to 1 given for set B. Alright. So y is equal to given as beta naught some q, beta 1 some q into x1 and all other terms beta 2 x2 plus so on up to beta k x2 side. This is the model which is given. Okay. Now it is given that effect of x2 to xk is same for both factors. So here we don't need to use any dummy variable. It's same for both factors, right? So if this is true, then we will not use dummy variable for this part. It will be as it is variable from x2 to all the way to x3, right? So we will only consider. So let us write. We will only consider the effect of x1, effect of x1 in the dummy. So how will we write therefore? We can write therefore the actual model as y is equal to beta naught as it is you just write. Just remove this q part. Beta naught as beta 1 x1 plus beta 2 x2 and so on up to beta k x. This part is fine. Alright. Plus. Now we have to use the dummy part into plus z into how much? Only these two variables has to be kept in the dummy because all other are same in both the factories. So we will not repeat it as your ninth question was there. So it will be only alpha naught plus alpha 1 x plus x. That's all. This should be my answer. Okay. Since x2 to xk are coming from the same factories, means is same for both the factories, we will not be using it in the dummy part. Only which is different, that is has to be used. That is the main point. So nice explanation is there in the 10th question. All right. So if you look at the 10th question, finally, it is the C beta naught plus alpha naught z plus alpha 1 x1 z and so on. All the things are there. So if you just uh, write it here, open it, so you will get the same thing. So beta naught plus just you write this. Okay, alpha naught z plus alpha 1, the interaction term x1 z plus and all our other terms beta 1 x1 plus beta 2 x2 and so on up to beta k x k plus x. That's it. This is the final answer. All right. So this completes our assignment part. Now we will quickly move to the polynomial regression part, and after that, after solving some of the concepts, then we will do some practice question. There is a question, so we will do that. Just a minute. Okay, so we will come to week 11 part, which is on the polynomial regression. So let's go to the next page. And, okay, so this is related to now week 11. So this week 11 is mostly depend on polynomial regression model. So far, we were using either simple linear regression model or multiple linear regression model. So we have not introduced the x squared term or x cube term in the last whatever lectures we have seen. Now, there are possibilities that your data set is such that it follows some kind of a non-linear relationship, right? So it can be possible that you have some data which is something like this, all right? So of course, you can still try to fit it as a linear fit in some sense, but you see that your r square value, we have discussed r square, right? So r square is the the coefficient of determination. This r square value becomes very small in this kind of a model. Then what we have to do is that, because if r square is very small, then it's not a very good model fit. Correct. So if r square is small, then and we are seeing that it's a kind of a nonlinear relationship. Then can we go for higher order model? Well, we now fit a quadratic kind of a model, something which is a parabolic kind of a shape, right? Quadratic model. So using quadratic model, you will find that this r square value will be increasing. That is, it is greater. So that's why in some kind of a data which shows a nonlinear relationship, you might see that it is helpful to bring the higher order, uh, higher orders of x, like x square, x cube, and all. Okay, x square, x cube, and like that. Okay, so let's come to therefore the polynomial regression model. For this concept is important. So y is equal to, how do we write it? Like this: beta naught plus beta 1x plus beta 2 x square plus xn. This what I have written is for this quadratic model. This is a quadratic model. The general model I will write. So this is the quadratic model, or you can write second order model in one variable. All in one variable. Just remember, model in one variable. Variable. All right. So in general, just remember for the beta naught, sorry, this quadratic model, this is called same intercept This is again the slope, and this is called the curvature. Okay, just for the second order model. Okay, let's now generalize it for the kth order model. So in kth order polynomial, you can write this as a polynomial. It's absolutely fine. In one variable only. We are not writing multiple linear model. Sorry, multiple regression model. It will be a single regression model. Okay, single regressor model. So one variable is therefore y is equal to beta naught plus beta 1x plus beta 2 x square plus so on up to beta k into a to the power x to the power k plus epsilon. All right. So this is the kth order polynomial if you have to fit using one variable. Remember, this is for the one variable. One register variable is there. Now, what we will do is that if we write if we write x of j as x to the power j, how will this equation look like? This will be y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Why? Because x2 is equal to x square. So this is fine. Plus so on up to beta k xk plus epsilon. So what we have done is that it is a kth order polynomial in one regressive variable, but we have transformed it into a multiple linear regression model. Okay, so we have transferred it to a MLRM, multiple linear regression model. Look at it. It seems that x1, x2 are they are multiple regressor variables, but actually it is not. In the background, you must know that it is only a single regressor variable, but it is a power. But it is only the representation in the multiple linear regression model. So once we have converted it, we will just use the multiple linear regression model to find out the coefficients. Okay. So yeah, so this are fine, and we generally keep the order of polynomial regression model to be very low. Okay? Polynomial regression model order of polynomial should be as low as possible. Possible. Generally, we try to make it by two, within two. Okay, we don't go for much beyond two, except for some conditions, some data sets. Okay, this is one of the things. Now, how to build a model? So, model building strategy is the next concept which is being discussed. Model building strategy. So, suppose you have you start with a linear model. Of course, whenever you have data, you always plot a scatter plot, right, between x and y. You plot a scatter plot between x and y and see how the data relationship looks like between y and x. All right, because it's a single regressor variable, so you can always plot it and see. All right. When you have plotted, you first fit a simple linear regression model, that is beta naught plus beta 1 x plus epsilon. Once you have fit it, check the significance of the highest order term. Check significance of highest order term. So, which is the highest order term here? X to the power 1 is the highest. So, beta 1. You check the significance of beta. If beta 1 is significant, then you go for the next order of polynomial. So, you go for y is equal to beta naught plus beta 1 x plus beta 2 x square plus epsilon to go for this model. Okay, again, so test the significance of highest order model. Okay, now if it is significant, if the highest order model its coefficient is significant, then you go for the next order. If not significant, then stop. Right? So this is what the model building strategy is. Okay. So now if you check that beta 2x square, suppose this is the data, you first fit a single straight line, which we have seen first. Okay. And you found that result. Beta 1 is significant enough, then go for the second one. So if it is now, you fit a model and you see that the beta 2 is now significant, then it's fine. Go for the third order. If it is not significant enough, then you stop it here. That is the final model. All right. So this is how you have to proceed. Okay. So next concept is the ill conditioning. Ill conditioning is just like the multicollinearity which we have discussed, let's say 2, 3 lectures before. So this is ill conditioning is very similar to the multicollinearity problem. Very similar to multicollinearity problem. So what it says is that as the order of polynomial increases, as the order of polynomial increases, what happens is that the x prime x inverse this becomes ill conditioned. That means what? There is a problem in calculating the inverse. That means it's going towards the singularity of x prime x, right? So become ill conditioned. All right. So what happens is that you know that your beta hat, because ultimately we are calculating the multiple linear regression model, this one. Okay, we have transformed into multiple linear regression model. So ultimately, we have to use this formulation. That is x prime x inverse x prime y. This we have to use. But for that, this has to be properly calculated. But you know that inverse always exists when the determinant of x prime x is not equal to 2. But when you do this kind of stronger or higher order polynomial terms, what happens is that if it also depends on the data set. If X is, say, having very narrow range, this example is I have taken it from the the lecture itself. So you have suppose X as this. Okay, first column is 1. Second is like this, 0.1, 0.11, 0.12, and so on. Okay, so this is X. Remember, so this is X0, this is X1. X2 is nothing but x square. Don't confuse it with anything else. X2 is x square. So what it will be? 0.01. This will be 0.0121 and so on. Next, x3 further 0.0001 and so on. So as you go for higher order terms, you will see that, in fact, you will see that x1 and x2. So you can find that x1 is nothing but 1 by 100 times x uh, sorry, x2 is 1 by 100 times x1. So there is a linear dependence. Okay, there is a linear dependence between the x1 and x2. I'm not writing regressor variable because this is only single regression. Single regressor variable is there. We are writing it in terms of multiple linear regression. Just remember. So linear dependence between x1 and x2. If this occurs, we have seen that the determinant of x prime x will tend to 0. And this arises the thus the singularity problem arises. And if this arises, then what happens is x prime x inverse is wrongly calculated or difficult to calculate. Difficult to calculate. And entire calculation will be problematic. Okay, so this is called the ill conditioning. But this happens when you have increased the order of polynomial. That's why it is advised to keep the order of polynomial as low as possible. Okay, but how we can remove this kind of linear dependence? So there is a process to remove this linear dependence is to use centering. Remember, in the multicollinearity concept, a similar thing we have done. We have used centering and then scaling. Here we don't use scaling. Here just we are using the centering method. Okay. By using to remove this, we have to use centering of the data. So centering of the data, as you will remember, that it will be just subtracting it from the mean value. That's all. So how we will write for removing this is y is equal to beta naught plus beta 1 x minus x bar plus beta 2 x minus x bar square plus epsilon. Right. So you will find that this kind of a question is there in your assignment 11. So just don't worry, just you have to calculate all these things, x minus x bar and x minus x bar whole square, whatever the model is given, you just do it like that and use the multiple linear regression model kind of a picture to calculate the slopes and intercepts, whatever, the beta naught, beta 1, beta 2, whatever. Okay, so that is all about the ill condition. Next concept is very important, which is the orthogonal polynomial, and we will be using, we will be calculating this orthogonal polynomial in a practice problem, which I will show after covering this concept. So, so let's discuss this orthogonal polynomial and why is it important. That also we will discuss. Okay, next is orthogonal polynomial. Why suddenly this concept arises? Why we require orthogonal polynomial? So all this we will see. So suppose we wish to fit the model this, that is y is equal to beta naught plus beta 1x plus beta 2 x square and so on up to beta k x to the power k plus epsilon. This is the model. Suppose we want to fit, and you have x. We know that how to write it. So there will be first column will be always 1, second column will be x, next x square, next x cube, and so on up to x to the power k. Correct? This is how we write. Now, all right, everything is fine. But suppose we want to add, okay, we want to add another term. What is the term? Suppose beta k plus one. Suppose since it is up to beta k x to the power k, let us add another term. This, okay, we need to sometimes. Now, if I need to do this, then remember all these beta naught, beta 1, beta 2, whatever we have seen for this model will not be valid for after adding this model. So what I try to mean is that suppose the initial model, what was that? Beta naught plus beta 1 x plus beta 2 x squared plus etc. This is one of the models. Suppose this is an example. Okay. So you fit this model using multiple linear regression model and you found out beta naught hat, beta 1 hat and beta 2. Great. Now we want now okay. We have seen that the x y data whatever is there to the to this second order polynomial fit it is not very good. We need to introduce another variable. So let's go for the third order polynomial. So beta naught plus beta 1x plus beta 2x square plus let us change the this plus beta 3 dash x cube plus x side. Okay, we change to this. Now you cannot use this. Okay, now this will be the beta naught dash hat, beta 1 dash hat, beta 2 dash hat, and beta 3 dash hat. These are the four coefficients. Important thing is that your beta naught hat will not be equal to beta naught dash hat. Similarly, beta 1 hat is not equal to this. Okay, then beta 2 hat is not equal to beta 2 dash hat. Okay, so this what it means is that you have to recompute for this model. So you have to recompute the entire process you have to do again and again to calculate these coefficients. This will not be equal to this. All right. So you have to recompute. The problem is that you have to recompute the X matrix, particularly X matrix again to recompute X matrix again for beta. Okay, so this is the problem which arises in general regression model to calculate the polynomial regressions coefficient, right? To deal with this, we have to go for the orthogonal polynomials. Okay, to deal with this, we go for orthogonal polynomial, and you will see that this orthogonal polynomial will not change. Okay, go for orthogonal polynomial. If we add one variable, the whatever the orthogonal polynomials we have calculated for suppose this model, whatever the orthogonal polynomials we will calculate, all those will be valid up to this, and the new will come, right? So that is the use of orthogonal polynomial. All right, so let's see that how to what is the definition of orthogonal polynomial and how to write those orthogonal polynomials. Then we will see how these orthogonal polynomials are defined. So, and then do some analysis and then do the practice question. All right, just give me a minute. All right. So, for the orthogonal polynomial, so let us write it. Suppose this P naught x, P1 x, and so on up to Pk x. These are the orthogonal polynomials. Are orthogonal polynomials if they satisfy the orthogonality condition. That is summation I is equal to 1 to n P r of xi into Ps of xi is equal to 0 for r. not equal to x. So P naught, suppose x1 into P1 x1, and you sum it P naught x2 into P1 x2, and so on up to whatever Pn. Oh, sorry, this is P naught xn into P1 xn. So as you can see that R and S are not equal. If you sum this, it will be zero. It will be only true when you have P naught x1 into P naught x1 plus P naught x2 into P naught x2, and so on up to P naught xn into P naught xn. This will give you whatever the value, that is summation of P naught square xn I is equal to 1. This will give. This will give you some value. But if this is 0 and this polynomial is of order 1, then it will be always 0. This is the what you call as the orthogonality condition. Okay. So you might have encountered it, this orthogonality of Legendre polynomials, then all those things. Quite similar to that. Quite similar to that, but the orthogonal polynomials, the definition is different. We will see that. Okay, that how to create the polynomial, how to generate the polynomials, that is different. Okay, so therefore we can write the model, the polynomial regression model, in terms of orthogonal polynomial in this way. We can write the model as yi is equal to alpha naught p naught xi plus alpha 1 p1 xi plus so on up to alpha k pk xi plus epsilon I. Remember, this is all based on the orthogonal polynomials, not based on the x square, x cube like that. You have to see that, or you have to see the relation of, say, some p1x with x. You need to know. So you need to know relation with this p1 x with x1, x square, or so on, whatever. Otherwise, we will not be able to write the actual model, right? Because ultimately, what we want y is equal to some beta naught into plus beta 1 into x plus beta 2 into x square. We need this finally. But what we are writing in terms of orthogonal polynomial. Just remember this. Okay. So you have to convert. Ultimately, you have to convert from p naught or p1 or pk, whatever the order of polynomial, to x square, x cube at the very end, not at this moment. Okay, so this alpha naught, alpha 1 are not the actual coefficients, beta naught, beta 1. They are the, I would say that some kind of a reduced coefficient due to the introduction of this orthogonal polynomial. Just remember this part. Okay, so we are actually replacing. So we are replacing x with p1 or x to the power k with pkx. We are replacing. Just remember this. We are not writing that this is actually x, this is not like that. Okay, so this is one of the things. Fine. So let's. One of the conditions of using this kind of a model is that condition is that x data must be equally spaced. Only then you can use it. Okay, it has to be equally spaced. Okay. Now let me give you the values. So P naught of x I is equal to 1. P1 of xi is equal to lambda 1 xi minus x bar divided by d. I will come to it. What is d? What is lambda 1? The upper part you will understand that this xi is the actual data set minus x bar is the mean. Okay. Next is P2 xi can be written as lambda 2 some coefficient into xi minus x bar divided by d its square minus n square minus 1 divided by 12. Okay. This is the second order polynomial, orthogonal polynomial. P3xi is equal to lambda 3 into xi minus x bar divided by d to the power 3 minus xi minus x bar by d into, I'm writing here, 3n square minus 7 divided by 12 to this. Maybe you have to go for this, but you don't need to go for the P4xi or something. You will see that the questions, whatever comes, is up to generally P2, not even P3. So next is P4xi. Still, I will write it. This is lambda 4. The first term is quite similar to whatever we have seen, d to the power 4 minus xi minus x bar by d square into, there is a term en square minus 13 by 4, and a last term comes, that is 3n square minus 1 n square minus 9 divided by 560. This is a big polynomial. But you don't need to go for this. Mostly up to P2 is fine. So we will see that there is a question where up to P2 you will calculate. Okay. So what is D? D is the spacing, which is equal spacing between levels of x, lambda j. It has to be chosen by us. Okay. Chosen by us to make the polynomial value polynomial value integer. Okay. Nearest integer, whatever. Not nearest, then you will say that let's round up. No, no, not like that. So to multiply this lambda 1 in such a way that the polynomial value becomes an integer value. Okay, so this is how it is done. So what we are actually doing, a algorithm step is that you start with whatever model you have. Y is equal to beta naught plus beta 1x plus beta 2 x square and so on up to beta k x to the power k plus epsilon. This is the starting point. What we have done, we have replaced it with y is equal to alpha naught into p naught x plus alpha 1 into p1x, so on up to alpha k into pk x plus epsilon. Okay. Now, for this kind of a model, same way we will do whatever we have done for multiple linear regression model, the same way. So the X matrix will be something like this. The first column will be 1 related to P naught X. Just see in the P naught X, its value is always 1. Okay. So these are all going to be 1. Next comes P naught X. Next is P1X. So you write the P1x values, you calculate using whatever is given. We will do one example, don't worry. So x2 up to P1 xn. Similarly, go for pk xn x. So it will be pk x1, pk x2, and so on up to pk xn. All right. So this is your x matrix. Similarly, your x prime will be what? Just this will be 1, this will be 1, so on up to 1. Just one row I am writing so that the calculation you will understand. X2, so on up to P1 xn. Okay, and so on. You can generate it. All right. So this is how it is written. So you can understand that this will be a n by k minus, sorry, k plus one matrix. Okay. So when you do x prime into x, what is happening? X prime into x. So this row, let me just change and show you. This row, entire row, is multiplied with this, right? And added, of course. This is a matrix multiplication. So x prime into x, matrix multiplication, will give you what? So if you now write here this x prime x, so 1 into 1, this row is multiplied by this. So what it will be? It will be n. Just the addition of these two, multiplication and addition. So it will be n, correct? Now, if you now see that this row, this particular row is multiplied by the second column, correct? Because x prime x next element will be that. Remember, this is nothing but p naught x. This is nothing but p1x. So we have seen the summation p naught x I into p1x I. If you say that it is an orthogonal polynomial, this has to be 0. So this all terms will be 0. Correct? Next, the second row, this multiplied by this. Again, same condition. P1 into P0. This will be 0. But this into this is nothing but summation P1 xi into P1 xi. This will be whatever the value. So it will be summation of P1 x square. Okay, xi you can write, and this is in. Similarly, this will be I P2 square xi. So on I pk xi square. All other terms will be 0. All right. So this is a very simplistic. So this is how the x prime x will be calculated. Very interesting. This is the diagonal matrix. The beauty of orthogonal polynomial is that when you do this calculation of x prime x, it becomes a diagonal matrix. And it's easy to calculate this inverse. What is the inverse of this diagonal matrix? Absolutely simple. That is just reciprocated. 1 by n, 0 and all. Then 0. It is just 1 upon summation of I, whatever you have, xi square. And so on. Okay. Only the diagonal elements will be reciprocated. That is the thing. Okay. Now, again, so you will have to do this x alpha plus epsilon. So I just wanted to show that how this x prime x inverse can be calculated. And then alpha hat will be equal to x prime x inverse into x prime y. Okay. So let's look at this particular part. So x prime y. Let's look at x prime y. So this will be what? X prime. So 1, 1, all. Then here p1 x1, p1 x2, so on up to p1 xn. 2 is enough, 2 rows. And you have here y1, so on up to yn. This is how the y matrix will be. So what it will be? This is nothing but x prime y will be the first term, this multiplied by this. So it will be nothing but summation y. I is equal to 1 to n. Right? Next term will be summation yi into p1 xi. And so on. Finally, it will be yi into pk xi. Right? This will be the x prime y. Now, this is x prime y. Remember, we already know what is x prime x inverse. Okay, so just the first term will be multiplied. So if you now write alpha hat, which is nothing but x prime x inverse into x prime y, just look at it. What is the first term? 1 by n. All other elements are 0. So just multiply by n. So it will be, so the first term will be 1 by n multiplied by whatever we have got. I is equal to 1 to n summation 1. Similarly, next will be this 1 upon summation p1 xi square. So it will be summation yi p1 xi divided by summation p1 xi square. Okay, and so on. You have to go ahead and finally you will write yi p k xi divided by summation pk square xi. All right. So you'll just clearly see it from this x prime x inverse and x prime y that this is how the matrix will look like. Okay. So based on this, we will try to solve one question quickly. So it is an important question. So before that, I will just write the how to calculate the SS regression and all these things, the generalized expressions, so that it is easy to calculate. Okay. So I think this step now is clear, which is, I think it was not, it was missing in that video lecture. But of course, if you do it on your own, you will be able to understand. So this is how the things are calculated. All right, let's go ahead for the generalized expression. Therefore, based on this, alpha j, some jth value of alpha hat will be then what? Summation I going from 1 to n, yi p j of xi divided by summation I going from 1 to n p j square xi. This is how the alpha hat has to be calculated. Okay, fine. Now, SS residual can be calculated from this SS total minus SS regression. So I'm just writing the value, sorry, the expression. So it's yi minus n y bar square. This is SS total minus SS regression can be written like this. J is equal to 1 to k because there are k order of polynomial alpha j hat summation yi into pj xi. Okay, this is how the SS total SS regression can be calculated. But if you have to calculate SS regression of each individual alpha, then you have to write like this. It will be alpha j hat into summation of I going from 1 to n pj xi into y. That's all. Okay. So if you have to construct an ANOVA table, so just I show quickly. For the ANOVA table, you need a source, degrees of freedom, SS, MS, and F. So source is all the variables alpha 1, alpha 2, so on up to alpha k. Then residual degrees of freedom and total degree. SS total. Each regressor will have 1 degree of freedom. Okay, this will be also one. But for the residual, it will be, see, there are k values, right? K regressors. So k degrees of freedom will be there. And the total will always be having n minus 1 because SS total is defined like this, which has one constant that is should be this is the one constant. That's why it is n minus 1 degrees of freedom. And this all total, if you add it, this will yield you 3 degrees of freedom. So residual will be n minus 1 minus k. All right. This will be SS regression of alpha 1, SS regression of alpha 2. How will you calculate? Based on this. Okay. So on. This is regression of alpha t. Then next is MS. So this is SS residual definitely. How to calculate MS residual? It will be nothing but this is regression of alpha 1 divided by 1 degrees of freedom. So in this way, you can calculate SS residual divided by N minus K minus 1, and F will be for each and every cases, you can write F as MS regression of some alpha j divided by MS residual. This is how the F can be done, and it can be compared with the F of numerator to denominator. That's all. Okay. So significance can be calculated. Significance of okay, significance of highest order term is that H naught null hypothesis will be alpha k. This is the highest order term, and H1 alpha k not equal to 0. Right? So this will be MS regression of alpha k divided by MS residual of full model. So it will be F of numerator will be having 1 degree of freedom because one regress that we have taken, and in the residual it will be N minus K minus 1. So this is how the test statistic has to be formed. So if F is greater than F1 comma N minus K minus 1 comma some 0.05 or 0.01 whatever you want, then you will say that it is that alpha k is significantly is significant actually, or significantly not equal to 0. Okay, so this is how the testing has to be made. Fine. So this is the part which is important, the orthogonal polynomial part. We will now do one practice question. Then, if time permits, then we will go for the introduction of the spline, that is cubic spline model, and polynomial model in two or more variables. Just I will write it down so that will be easier. Okay. So let's do some practice questions. See the questions first. Okay. Now, some practice question. So the question is, or the data set is, let me write the data set first, and then we will do one by one. See, this is an observation, then X, then Y, and okay, let's first write this. I'm writing it first. So there are 10 observations. All right. You have 50, Y is 335, 326, 316, 313, 311, 314. That's all. So this is the data which you will be given. Okay. Question is that now that you fit a second order model using orthogonal polynomial. So it's clearly mentioned that you have to use the orthogonal polynomial model. Okay. So when you have been used this, so you can just leave it as it is as y is equal to alpha naught p naught plus alpha 1 p 1 and so on. Okay. You don't need to convert it into beta naught plus beta 1 x and plus. Okay. So what is that model? Is y is equal to alpha naught p naught x plus alpha 1 p1 x second order, right? So it will be alpha 2 p2 x plus epsilon. As I have told you that up to 2 order of polynomial is mostly required. Okay. Based on this, so you fit first and calculate the best estimate, sorry, the least square estimate of alpha naught. So, of course, if you fit the model, you calculate alpha hat. From there, we will do something. But you first have to fit the model. To fit the model, that orthogonal polynomial model, you need P naught x, P1x, and P2x. Then only you will fit, right? Because ultimately these coefficients are required. So I will write it here with some other color. This is P naught, this is P1, and this is P. So P naught is very easy, always one. So no need to worry about this. It's always one. P naught xi is always one. P1. This is important. So how to calculate the P1 xi? So what is the formula of P1 xi? Let's see. This is xi minus x bar divided by d into lambda 1. This is what it is. Okay. Now d. What is d? The spacing between the x. See, these are equal spaced. Very important. So the difference is 25. Now another thing is that you may use this also. Okay, this is also fine. These are also equally spaced. Instead of using 50, 75, 100, and 125, you can use 1, 2, 3, 4, 5, 6 also. The result will not change. Just remember it. So whenever if you are using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, use the average value of this, not this. Okay. So you can see, I will show you that the difference and the polynomials will not change. Okay, but let us first do it using x. Okay, fine. So d is, let's say, 25. I'm using the x, whichever observation is given. X bar, that is summation of x by n. I have calculated already. This is 162.5. You can calculate also. Okay, you can add all these values and divide it by 10. Now, so let's first write one of the observations. Okay, p1 of x1. So what is x1, by the way? Let's keep it lambda 1 for the time being. What is x1? 50. So it is 50 minus 162.5, which is the x bar, divided by 25. Correct? So let's keep the lambda 1 because it's my choice. I will put it later. 50 minus 162.5 by 25, if you do, it comes out to be minus 4.5. What I should do to make it integer? Just multiply by 2. So choose lambda 1 is equal to 2. And what you will get is that P1 x1 is 2 times minus 4.5, which is equal to minus 9. Okay. Now, once you have fixed the lambda 1, for all other calculations of x2, x3, x4, you will not change the lambda 1. It will be same. Okay. And you will see that the values will come such a way that 2 is a good fit, means good choice. Okay. So P1 x1 is this. Okay. Let's do one thing. P2 x2 let us see. So what is your x2? 75. Let's do it. So lambda 1 is already defined 2. So it is 75 minus 162.5 divided by 25. When you do that, you will get this as minus 3.5. So 2 into minus 3.5 is minus 7. So you will get the integer always if you choose same lambdas. Okay. So in this way, you can calculate further. So P3, sorry, it's not P2, it's P1. Till we are doing P1. X3 is 2 times whatever. Next it will be 100 minus 162.5 divided by 20. That is equal to 2 into minus 2.5. So it's a 1, you can see that it is reducing by 1. So it will be minus 5. Similarly, so you can calculate further. Okay, dot dot dot. I'm just writing. So I will just fill up this. lengths of P1. So you'll find that this is -9, this is -7, -5, -3, -1. Then after this, no, it will be just repeating, but with a positive sign. So 1, 3, 5, 7, 9. You will see that when you start calculating, you will understand that this will be repetition. Okay, so this is how the P1x are calculated. Great. Now let's go for P2x. What is the formula of P2x? Is equal to lambda 2 into xi minus x bar whole square divided by d square minus n square minus 1 by 12. All right. So n is known, n is 10. So not to worry about that also. Lambda 2 I will choose later. Let's calculate 1. So x1 is equal to 50, right? So lambda 2 is equal to, look, this we have already calculated, xi minus x bar by t. How much it is? We have seen that it is minus 4.5 square minus n square minus 1. This, if you calculate 100 minus 1, 99 by 12 is actually 8.25. This will not change. For each cases, x2, x3, x4, this will not change. Okay, so you have lambda 2 and this will be your, I think, 20.25. If you do it, it will be 20.25. And if this comes out to be 12. So the only choice of lambda 2 is that choose lambda 2 is equal to 1 because already integer is there. Therefore, P2 of x1 will be 12. Let's calculate another and then we will leave out. X2 is 75. Okay, so it will be lambda 2 is 1, so not to worry. So this will be 75 minus 162.5 divided by 25. This also we have calculated minus 8.25. This will not change. This we have calculated to be how much? Minus 3.5 squares. Minus 3.5. This gives you the value is 4. Okay. So in this way, you can finally calculate all others. Okay. So I just fill up the values. It will be 12. This will be 4. This is minus 2. This is minus 6. Minus 8. Minus 8. Again, you will see the repetition. Minus 6. Minus 2. 4. 12. So this is how the P2 x are calculated. Now, just one point. If you don't use this x, you use this. Okay. So you will find that the average value of this observation, say let's be x dash. So x dash bar, you will find out that this is equal to 5.5. Now, just look into it. The difference d in this case is 1. Okay, I'm using x as this observation part. So d is 1. Okay, so now if I do this thing, xi minus x bar by d, look at this. So first observation is 1 minus 5.5 divided by 1. How much it is? Same, minus 4.5. So am I getting the same answer? Yes. Okay, same. So lambda 1 has to be chosen as 2, and in that way you can calculate. So even if you use, instead of using x so many large values, if you want to use this, it's fine. Okay, so that is the thing here. Well, now we have calculated P0, P1, Px. We are easy to calculate alpha j hat. We don't need to do x prime x inverse x prime y. Here we have already a formula derived from that. So we'll use that. So what was the formula? It was Pj xi into yi I in summation, and you have Pj square xi. That's the thing. Okay. We need to find out alpha naught. So let's do it. So I is equal to 1 to n. So n is with 10. So it will be P of 0 xi into yi divided by P0 square xi. So you know that P0 square is nothing but 1. So all are 1. So what it will be? It will be 3. This will be, again, if I write it properly, it will be 1, always 1, right? So it will be yi divided by summation of 1, I is equal to 1 to 1. So it will be nothing but y bar, correct? Y. So this will be y bar. So y bar is what? So you can calculate y bar. This will be 324.3. Okay. Therefore, alpha naught hat is nothing but 324 point. This is first problem. Next is alpha naught hat is calculated. Let's calculate one more. Calculate, or two I can say. Calculate alpha 1 hat. So same formula, alpha 1 hat will be summation P1 x now into yi divided by summation P1 square x. Alright. So how will you do it? So alpha 1 hat will be simply, it will be 335 into minus 9 plus 326 into minus 7 plus so on up to 345 into 9 in the numerator divided by minus 9 whole square plus minus 7 whole square, so on up to 7 square plus 9 square. What am I doing? Is this. You might have understood this 335 into minus 9, 326 into minus 7, and so on. Okay, in the numerator. And in the denominator, all the P1 values which we have computed, square and add. So alpha 1 hat becomes 245 in the numerator, denominator is 330, comes out to be 0.7424. Okay. Similarly, do alpha 2 hat. So third is calculate alpha 2 hat. So alpha 2 hat is similarly P2 xi into yi divided by summation P2 square xi. So I'm just writing, you might have understood that how to do it. So it's 335 into 12 plus 336, 326 sorry, into 4 and so on up to 345 into 12 divided by 12 square plus 4 square plus so on up to 4 square plus 12 square. Once you do it, you get 738 by 520, comes out to be 1.39. Okay. So that is what it is. So your y hat therefore will be something like 324.3 into P naught x plus 0.7424 into P1x plus 1.397 into P2x. That's all. And when you will change it into beta naught, beta 1 or beta 2, you have to just replace. P naught is what? 1. P1 is lambda 1, x minus x bar divided by d. So you have to keep the x bar and d, you can put it here. Okay, in that way, you will find out that what will be the beta naught, beta 1 and beta 2. Okay, so this is the answer, fitted model. Next question is the fourth one, based on the SS regression. So calculate SS regression of alpha 1. So what it will be? We have seen SS regression of a particular regression coefficient is alpha 1 hat into summation of P1 xi into yi. Okay, so it will be I is equal to 1 to 8. Alpha 1 we have calculated, And this is also calculated here, where it is this one. All right, so this will be 245. This is 181.89. Similarly, fifth is calculate SS regression of alpha 2. That will be simple. Alpha 2 hat into summation of yi into P2 SL. So all these things are calculated, so you can always do it. 397 into 738. This gives you 1030.98. All right. So now what you need to do is that, can you calculate the SS residual? So calculate SS residual. So how to do it? Anyway, you can do it. See, SS regression total means for alpha 1, alpha 2 adding on for the entire model. This will be nothing but SS regression of alpha 1 plus SS regression of alpha 2. There will be no SS regression of alpha naught because P naught is 1. Okay, so it will be about 1212.8. Just add these two. So this will come. What about SS total? Is yi minus y bar whole square, can be written as summation yi square minus in y bar square. So you can calculate all these things. It comes out to be 1240.1. And from here, SS residual can be calculated. How? It is a definition. SS total minus SS regression. So it's 1240.1 minus 1212.8. How much it will be? 27.2. All right. And the final is about the significance, that is, say your null hypothesis H naught is alpha naught is equal to alpha 1 is equal to 0, and H1 is that H naught is not true. So you test the significance of the alpha naught and alpha 1, okay, whether they are really significant or not. To do that, you have your F statistic, but you have to use extra sound square. So it will be SS regression of the full model minus SS regression of a restricted model divided by the degrees of freedom divided by SS residual of the full model and divided by 10 minus how many? 3. Because your in the entire model you have alpha naught, alpha 1 and alpha 2. So 3 unknown parameters. That's why this is the degrees of freedom. Alright, so for full model it is 1212.88. And for the restricted model, what is the restricted model by the way? Sorry, this is alpha 1. I'm sorry, alpha 1 and alpha. So what is the restricted model? Y is equal to alpha naught plus epsilon. Sorry, P naught x plus epsilon. P naught x is 1 always. So this is SS regression of this will be always 0 divided by. So how many the degrees of freedom will be? 2. Correct? And divided by 27.22 we have calculated divided by 7. So you just do it F your 2 comma 7, and you can check for 0.05. Of course, this is very strong value, you can see. So always F is greater than this. So you need not to calculate also. It's very strong. 1212 divided by this is even a smaller quantity. So the calculation of this F is 155.9. Okay. So this is the thing. Also, another question is there. The last one. It asks that can the second term, second order term be deleted? Can the second order term be deleted? Which means alpha 2 is 0 or alpha 2 is not equal to 0. This is the test you have to do. If we have to accept the null hypothesis, then it can be deleted. Correct? So F will be simple. MS regression of alpha 2 divided by MS residual of the full model, which is SS regression of alpha 2 by 1, because degree of freedom of each SS regression is 1, SS residual by 7. So you get 1030.96 divided by 3.98 or 89. That is F1, comma 7. You can write 0.01 or zero point 0.05, whatever. So it will be 265, which is much greater than 5.5. This shows that you can't delete. So second, so alpha 2 can't be deleted. That's all. So these are the practice problems which you have. Okay. All right. So you must have got an idea of how the questions on orthogonal polynomials will come. However, in the assignment questions, you will have to fit a simple linear, the polynomial regression model, that is multiple linear regression model. So you don't need to worry about this. But even if it comes in the exam original, the final exam, you can be you will be able to do it. Okay. So just I quickly go through 2 3 concepts. 10 minutes is enough. So I can show you. First, let me not discuss the spline one. Let me discuss polynomial model of, in two or more variables. How to do it, how to approach it. Okay. By the time we are doing it, these are all one register variable. Now it will be two. So it will be y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 1 x1 square plus beta 2 2 x2 square and plus beta 1 2 x1 x2. So there is an interaction, you can see it, x1 and x2. So this is the polynomial quadratic model, or you can say polynomial model of order 2, 2 degrees with two regressors. Okay, so you will find the linear effect parameters from beta 1 and beta 2, because these are related to the linear part. Quadratic effect parameters will be from beta 1 1, beta 2 2, and the interaction effect is coming from beta 1 2. Okay, so how will you do it? So same way, the way we always used that. So 1, this will be x1, x2, x1 square, x2 square, and the interaction x1, x2. This will be your x matrix. In the same way we do in the multiple linear regression model, we'll be doing the same, x beta plus epsilon. And you know, beta hat will be x prime x inverse x prime y. So nothing is changing, everything is same. So beta hat you will get what? Beta naught hat, beta 1 hat, so on up to, okay, let me write beta 2 hat, beta 1 1 hat, beta 2 2 hat, and beta 1 2. Okay, yeah, so these are the values which you will get. Okay, and if you have to do the test, significance test for significance of the entire regression of the regression model, so you don't need to use the extra sum of square because it is not the path. It's the entire regression model test you are doing. So h naught will be beta 1 is equal to beta 2, beta 1 1, beta 2 2, beta 1, 2, in fact, beta naught, it all are 0, and h1 is h naught not is not 2. In this case, enough is to do this. N is regression divided by n is residual, which will be f of regression degrees of freedom, comma, residual degree, and the significance whatever you want. Okay. So if f is greater than n, regression degrees of freedom, residual degrees of freedom, comma alpha percent of significance level, then H1 is accepted and significant. The entire regression model is significant. Fine. So this is one of the things. And okay, sometime is there, so we can just discuss the line part, although it is discussed in the uh, main video lecture notes also. So the last topic is then the piecewise polynomial fitting. Since time is there, so I'm just going here. Okay. So when we will be using when functions behave differently in different parts of X. So X, there are a lot of data. So you can see that there is a sudden change in the X values. There you will be using this. Okay. So spline, cubic splines actually are piecewise polynomial of order k. Generally we use cubic spline, so order will be 3. Okay. And join point, that point from where the x change suddenly, those join points are called knots. Okay. Knots. And finally, we generally use the cubic spline. That is k is equal to 3, which is adequate. Means you don't need to go further. Okay, so the spline, cubic spline polynomial is written like this: s of x summation j is equal to 0 to 3 beta 0 j x to the power j plus I going from 1 to h. H is the number of knots. Okay, I to h beta I x minus ti to the power q, and this is a plus sign. Okay, so ti is where the knots are there. Okay, so x minus ti plus is defined as x minus ti when ti equal x is greater than t, and it is 0 if x is less than equal to t. This is the definition of x minus ti plus. So suppose h is equal to 2, that you have t1 and t2 are the two knots. Okay, number of knots. It will be arbitrary. It's your choice in the data. You have to see and put it. A good example is given in the lectures, video lectures. You can see. So suppose A to B, there are two knots T1 and T2 in the entire range of A to B. So if it is A, X is lying in between A and T1, then you can write Y is equal to beta 0 0 x 0 plus beta 0 1 x plus beta 0 2 x square plus beta 0 3 x cube plus x. Nothing. So, so since x is less than t1, you cannot use. So this term will be 0. All right. Next, if it is lying between t1 and t2, then the part will be active. So it will be x to the power 0. Same thing. You have to write entire plus beta 1 into x minus t1 cube. And if it is t2 x to b, then all the terms will be there. So y will be same. Beta 0 0 x to the power 0 I'm not writing 0 1 x plus beta 0 2 x square plus beta 0 3 x cube plus beta 1 x minus t1 whole cube plus beta 2 x minus t2 whole cube plus x because x is greater than done. So to be remembered, the number of nodes should be less. That is h should be less. 2 is enough. Okay, so once you have this model, you can easily fit in the same way we do in the multiple linear regression model. So it will be 1x, x square, x cube, then x minus t1 cube and x minus t2 cube. All right. So based on this, you can put the values. So this is plus, this is also plus. That means you have to choose wherever you will find some zeros, somewhere there will be some value. Finally, this we know this is all the things we know. So beta hat will be how much? So this will be beta 0 0 hat, beta 0 1 hat, beta 0 2 hat, beta 0 3 hat, beta 1 hat, beta 2 hat. That's all. All right. So this is how you have to fit the lines. Spline model has to be used when you have this. There are different paths are varying in a different way. Okay. So that's all. So first, actually, you have to check cubic model using orthogonal polynomials. Okay, so this is one first part. Then check residual plot of this. If residual plot looks non-linear or not, so this kind of plot, if it is not there, ei is equal to 0. This is yi I have, and this is ei. So you are not seeing in a perfect band, so these are going away. Then you have to go for cubic spline. And if you then check the residual plot again, you will find that now it is much better. Okay, so this is how the technique is to be used. Okay, with this, I think it is enough today. We can stop here. So we have discussed several problems, uh, how to deal with the orthogonal polynomials. Although I think in the assignment it is just a polynomial regression, so it will be easy for you. So that's all. We have discussed the concepts, how we are getting this alpha hat and all those things we have discussed. So if any questions there, please ask. Yes. Hmm. Yes. Mhm. Yes. Okay. So okay. 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 Let me see. Uh, so SS regression of the full model, if you see uh, how much it will be. So suppose this is 7. So n minus 1 is how much? So 10 minus 1 is 9. So for SS total, the degrees of freedom is 9. And for SS residual of the full model, the degrees of freedom is 10 minus 3, which is 7. So your regression model, okay, the SS regression for the full model, it will be 9 minus 7, which is 2. Okay, so SS regression for the full model is 2. But if you look at the SS regression of the restricted model, only alpha naught is there. And corresponding to alpha naught, your SS regression will be 0. That's why it is 2 minus 0. So degrees of freedom is 2. Understood? Yeah. Because P naught x is always 1. So it's nothing. Just like beta naught. Okay. So that's it. Right. Right. Exactly. Exactly. Yes. Okay. Okay. Any other doubt? Okay. Thank you. Then we can stop today.